Microgrid islanding detection with a hybrid method. Abstract. As the fast integration of distributed generators is developing rapidly, it has become mandatory for the microgrids to be more stable and controllable to feed the loads connected, uninterruptedly. The general condition of any microgrid is in synchronism with the main grid in a normal way. This is also as per the Department of Energy of United States of America. The IEEE 1547 standards also say that the microgrid must have the robust islanding detection method, incorporated in the interfaced inverter, to detect the fault within the time duration specified. For this purpose an efficient islanding detection method, which is a hybrid technique utilizing both passive and active islanding types is proposed in this paper. The passive one is, rate of change of frequency, RCOF, and the active type is reactive current injection at inverter output terminals. The islanding detection is achieved with the cumulative sum of rate of change of frequency, RCOF. With this method, the low active power mismatch at point of common coupling is also compensated and the islanding detection is achieved in the specified time as prescribed by the standards. With all these controls embedded, the false detection and tripping of the microgrid, islanding from main grid is avoided. The non-detection zone area is also substantially reduced. The proposed methodology has been tested in MATLAB/Simulink environment and the results prove the efficiency of the method. Keywords: RCOF, rate of change of frequency, XROF, cumulative sum of rate of change of frequency, NDZ non-detection zone, DG distributed generation, reactive current injection, PCC point of common coupling, ID islanding detection, RES renewable energy resources, DIR distributed energy resources, DFIGW fed induction generator. Introduction. Modern power systems are becoming active networks with the introduction of RES. The microgrids are becoming bidirectional because if excess power is available after supplying to loads, the power can be exported to grid. As the power systems are modernized due to the presence of power electronics-based inverters, protection is developed to suit to the non-inertial DGS. But there are some more areas like transition states. They are grid to islanding and islanding to grid modes 1, 2. The islanding detection is more crucial, a safety aspect and stability concern is involved. If there is any fault in the main grid, it is to be sensed and microgrid has to switch over to islanding mode seamlessly so that there is no interruption of power to microgrid loads which are termed as essential 3, 4. These are also called unintentional islanding. Intentional islanding is, when maintenance work is to be performed either on grid or microgrid, the microgrid is to be isolated from main grid. This isolation of microgrid is achieved through a hybrid islanding detection technique of both passive RCOF and active reactive current injection at inverter terminals. The islanding detection becomes easy if there is mismatch between generation and load. But if there is no different supply and demand during islanding, the passive methods do not detect the islanding phenomena and hence NDZ occurs. At this juncture exactly, the active islanding detection technique to identify the islanding condition and to isolate the microgrid is a must. This will bring the microgrid stability and safety is ensured. The active islanding method of injecting a small reactive current into the system parameters like voltage and frequency. When grid is available these disturbances are taken care of. But in the absence, care is to be taken on the stability of the microgrid 5, 6. The positive RCOF technique cannot sense, if the deviations are below 15% active power at PCC. Hence an active islanding detection of small reactive current injection at inverter terminals is used, so that the power quality is not disturbed. This is a hybrid technique which combines both passive RCOF and active reactive current injection. If this small percentage is not enough, it is slightly increased to detect actual islanding. Hence the zero active power mismatch is also achieved to detect islanding by shedding the local load and bringing the load frequency to 50 Hz 8,9. A periodic small value of reactive current with frequency less than system frequency is injected to grid-side converter. The drift is sensed by RCOF. The XRCOF is measured for 50 milliseconds. If the XRCOF is beyond threshold value, the magnitude of reactive current injection is increased and XRCOF is again compared, to confirm the islanding state. This method avoids nuisance tripping of microgrid without actual islanding condition. The RCOF detects islanding if active power mismatch is above 15%. But with the hybrid methodology, RCOF and XRCOF efficiently detects the islanding condition 10,11. 2 Literature survey. The heart of any microgrid is the controller. The controller must be capable enough to keep the microgrid stable in grid mode, to be stable in transition from grid to island mode, stable in island mode and must be ready to synchronize to grid again for exporting and importing for economical benefits 7. Nowadays, the microgrids may be owned by consumers and they can become prosumers by supplying power to another microgrid with agreed tariff arrangements. A thorough review is done with references indicated below. It is suggested a method of intentional islanding. He has very elaborately pointed out different modes of inverters. Under grid connected mode the inverters should be CCM mode to share the loads proportionally. But in island mode they will revert to VCM mode to maintain constant voltage and frequency at PCC 21. It is also pointed out different scenarios of photovoltaic and windmill sources during grid, island and transition states 22. It is discussed in the reference about MPPT and battery control. He has suggested different maximization techniques like VF, PQ methods. 24. A special controller is proposed, which detects both positive and negative sequence components during unbalanced faults 23. A remarkable work is done by focusing on stability during grid mode only. The modeling was done in PSCAD/EMP platform 25. Discussed in the reference, about the stability of three-phase grid connected in island mode with linear load with and without anti-islanding controller 26. The author discussed about voltage source inverters with DGS about control of constant voltage and frequency 27. Pointed out different scenarios about stability during islanding when grid fault occurs and after islanding also 28. Reference paper also discussed about different protection methods against different faults 29. 3 Hybrid islanding detection method. The RCOF detection of islanding cannot work for active power mismatches between 0 to 15%. The frequency variation is not much enough for RCOF to detect islanding condition at PCCIB this condition. This is passive detection method of islanding detection method 12,13. To counter this gap an active islanding detection method of injecting reactive current at inverter terminals while in grid mode still. There is drift in frequency only under islanding. Otherwise there is no effect in frequency if grid is present. But setting a low value gives false tripping signal and at the same time higher value increases NDZ 14,15. But in this paper a low value of 1% of reactive current is injected with 30 Hz at Q-axis control of inverter at PCC. Precaution is taken to keep the reactive current injection value as low as possible to see that the power quality is deteriorated. This low value reactive current injection is not a matter when the active power mismatch if high. But the frequency drift is very small when the active power mismatch is low or 0. So for such small deviations, which are within the zone, microgrid need not be island. Hence the real scenario is identified 16,17. For small variation of frequency the RCOF cannot identify the islanding. The disturbances may be due to load switching transients. But to get exact islanding condition RCOF index is used for a time period of 50 milliseconds with a discrete model. The islanding detection algorithm is shown in figure .1. If the threshold value of Xrokov crosses the value and the frequency goes beyond the range, then islanding is detected and it indicates that the cative power mismatch is high. During low active power mismatch, Xrokov crosses the threshold value within the frequency range. The islanding may be because of some switching transients, hence islanding is not activated, which is the realistic scenario. Reconfirmation is done through injecting reactive current of 5% at 30 Hz. If the Xrokov computation value for 50 milliseconds exceeds threshold, confirms the islanding. For non-islanding, the value does not cross 18,19. For MATLAB system model. The system parameters are shown in table point 1. A PWM-based AC/DC/AC IGBT converter/inverter is the interfacing inverter of DG20. DG feeds a load of 5 MW at 50 Hz. The MATLAB simulation model is shown in figure point 2. The circuit parameters are shown in table point 1. The grid-side inverter is synchronized to grid via PLL. The loads and DG are adjusted for zero mismatch active power. The reactive E power is adjusted to 0 var. The circuit breaker is operated to create islanding. The worst scenario islanding is simulated and the islanding technique is evaluated. The results discussion. The sample time is 1.5 SECS and the number of samples per 50 milliseconds is 1000. The islanding is done at 0.8 SECS. It is clear from figure 3 that Rykov gives correct sensing for more than 15% active power mismatch. But for 0% mismatch, Rykov technique failed. Islanding is created as a stiff grid, cative power mismatch is 0 and reactive power is set to 0 var. Even during worst condition of islanding, the Rykov has not responded without reactive current injection of 0%, 1%, and 5%. Figure point 6 shows the increased trigger signal from 0% with a frequency of 30 Hz to 5% detects the islanding. Figure point 7 injection of 5% reactive current injection at inverter terminals, detects the islanding. At 0.85 SECS Xrokov after 5% reactive current injection detects islanding. As shown in figure point 8, islanding is detected with Xrokov at 0.85 SECS. Xrokov suspects islanding at 0.9 SECS due to increased to 5% injection of reactive current. Hence the Xrokov actually detected real islanding even at 0 active power mismatch. The technique is implemented with 50 MSECS window and with a time duration of 100 MSECS. The proposed methodology is robust, which segregates nuisance tripping with reactive current injection. 6 conclusions. The proposed hybrid method of Rykov with reactive current injection in Xrokov successfully islanded the microgrid within the stipulated time of 2 SECS as per the IEEE 1547 standards. This also avoided the nuisance tripping which is mandatory as per standards. Future work can be on the lines different combinations of hybrid detection methods with hybrid RES.